Hello and welcome students to my channel. Today we are going to learn the lesson real numbers. So real numbers play a very important role and we know what are real numbers? Everyone knows. Any number we see 1, 2, 3, 4, minus 1 by 2, minus 2 by 3, root of 2, root of 7.9. Any number that exists with us that we use in our daily life is a real number, right? So we are going to learn about the real numbers. Okay, let's see what we're going to learn in this lesson today. So what are the learning objectives? In this lesson, you will learn fundamental theorem of arithmetic. So we're going to deal with this theorem, which is very important in the number system. For the number system, we learn about the prime factorization of the numbers, right? So we're going to learn about this theorem. Then we have relation of HCF and LCM, which is highest common factor and least common multiple. Okay, what are composite numbers, prime numbers, and what are co-prime numbers? We're going to learn this. Okay, also rational numbers and irrational numbers. We are going to revise what are rational and irrational numbers and how do we know what is a rational and irrational number. Okay, and we are going to finally learn, which is the most important topic of this lesson, which is proof of irrationality. That is, how do we prove that a particular number is an irrational number? Okay, let's start. So now let's first see what are prime and composite numbers. So students, you might know that what are composite numbers? Composite numbers are natural numbers that have more than two factors. More than two factors. So now what is factor? What is factor? Factor is a number which divides a given number, right? If I take an example, if I say 8, can you tell me the factors of 8? Yes, so it is divisible by 1, it is divisible by 2, it is divisible by 4, and it is divisible by 8. So these are the factors. And you can see how many factors does 8 has? Of course, it is more than 2 factors. It has 4 factors. So is 8 a composite number? Yes, so 8 is a composite number. So I hope it is clear. A composite number is a natural number which has more than 2 factors. Okay, now let's see what is a prime number. A prime number is a natural number which has exactly 2 factors, which include 1 and the number itself. Let's see an example. 2, can you think of 2? How many factors does 2 have? 1 and the number itself, 2, right? Similarly 3, 1 and 3. Similarly 5, 1 and 5. They all have exactly 2 factors. So what can we say? They are prime? Yes. So these 3 numbers are prime numbers. Now let's discuss one important thing, that is about 1. What is 1? Can you tell me? Can you think, is 1 a composite number or a prime number? No. If I go with the definition of composite number says a natural number which has more than 2 factors. So do you know how many factors of 1? Just 1, that is the number itself, right? So it doesn't have more than 2 factors, neither it has exactly 2 factors. So we can say that 1 is neither a prime nor a composite number. I hope this is clear. This is very important because students get confused. 1 is neither a prime nor a composite number. Okay, let's move forward. Yes. So now we are going to see what is the fundamental theorem of arithmetic. What does it say? Every composite number. So here we are going to learn about the composite number, which can be represented. Okay, every composite number can be represented or factorized as a product of prime numbers. Okay, so it is written ki every composite number. Like if I take an example, if I take 8, so if I do the prime factorization of 8, 2, 4, 2, 2 and 2, 1. So we can write 8 as 2 times 2 times 2. Or you can say 2 to the power 3, where 2 is a prime number, right? If I take another example, 12 suppose. If I write 12 and do the prime factorization of 12, right? So what am I getting? 2 into 2 into 3. So here I'm getting 2 prime, that is 2 and 3. So every composite, and we know that 2 12 and 8 are composite numbers. We saw it previously, 8 has 4 factors and 12 also has more than 2 factors. We can count that 1, 2, 4, 3 also, right? 6 also. So there are more than 2 factors, of course, of 12. So they both are composite numbers and they can be represented in the multiplication of a product of the prime numbers, right? So this is what the first part of the theorem says. And what's the second part? Let's see. And this factorization is unique. Okay, so the representation of the composite number as a product of prime number. Each composite number has a unique representation in the form of the prime numbers, product of the prime numbers. Okay, so it means that 8 cannot be represented in any other way. We can write 8 as 4 into 2, but is it the representation in prime? No, because 4 can be further written as 2 times 2 times 2. So it has the unique representation as 2 to the power 3. Right? And apart from the order, so order does not matter. We can take the order in any way. I can write 12 as 3 times 2 times 2 as well. This makes no change. But we cannot write 12 as 6 into 2. This is not the prime factorization, right? The prime factorization involves that composite number must be written as a product of prime numbers. I hope it is clear. Let's move forward and see a question on it. Based on it, question how we use the fundamental theorem of arithmetic. Okay, so the question says, check whether 6 to the power n can end with the digit 0 for any natural number n. It's saying we have to see that 6 to the power n, can this number ever end with a digit 0? So can you think how we will proceed with this question? So 6, if I think about 6, so here n is natural number. So n belongs to natural number. We all know what is natural number. 1, 2, 3 and so on, right? Okay, so we can think about 6 to the power 1, 6 to the power 2, 6 to the power 3. If I think about 6, how can we write 6? 6 is 2 times of 3. This is the prime factorization of 6 and this is unique, right? Now think of some number which ends with the digit 0. Let's think smallest number 10. What is the prime factorization of 10? 2 times 5. Okay, so you can see this prime factorization of 10 contains 2 primes, that is 2 and 5. Right, let's see one more number, 120. If I think, let's see the prime factorization of 120. 2, 60, 2, 30, 2, 15, right? 3, 5 and 5, 1. So you can again see how can we write the prime factorization of 120? 2 to the power 3 into 3 to the power 1 into 5 to the power 1. Again, you can see the prime factorization contains 2 as one of the primes and 5 as one of the primes. So you can see that any number which is ending with the digit 0 contains 2 and 5 in the prime factorization, right? But 6 does not contain. 6 contains 2, but it does not contains 5, right? So it does not contains 5. So we can say that 6 to the power n will never end with the digit 0. We can say 6 to the power n will never end with the digit 0 because the numbers, or we can say the natural numbers, that have 0 as their end digit or unit digit are divisible by, you can say they are divisible by 2 and 5. Right, they must be divisible by 2 and 5 both. Okay, so but here you can see that 6 is not divisible by 5. 6 is not divisible by 5. And what is the use of the arithmetic fundamental theorem of arithmetic here? It is that we know that this prime factorization is unique. 6 cannot be, and using the fundamental theorem of arithmetic, we know that 6 is equals to 2 times of 3. This prime factorization is unique, right? So we are never going to get 5 in the prime factorization of 6. So we can say that it will never end with the digit 0. I hope it is clear. Very good question, conceptual question, in which you need to understand what is the real meaning of the fundamental theorem of arithmetic and how do we utilize it. And the most important result that we got here is that, let me highlight it. This is the most important. The natural number that have 0 as their end digit, they are divisible by 2 and 5. They can be divisible by any other number as well. Like you can see here, it is divisible by 3 also, but it must be divisible by 2 and 5. Or it must have 2 and 5 in the prime factorization as the primes. Okay, so this is very important. I hope it is clear. Let's move to the next topic now. Let's see what we have next. Okay, so now we are going to learn about the relation between the HCF and LCM. So what is HCF? Let's see. The HCF of two natural numbers A and B is the largest natural number that divides both A and B. Divides both in A and B, you can get an idea. It is the factor, right? Divides means factor. It means that it divides the number, both the numbers. So if I take the example again, if I take 8, what are the factors of 8? 1, 2, 4 and 8. Okay, what are the factors of 12? 1, 2, 3, 4, 6 and 12. So can you tell me what will be the HCF? Highest common factor of 8 and 12. So what is the HCF of two numbers? It is the largest natural number that divides both A and B. What is the largest natural number we can see here? See, 1 divides both, right? 2 divides both, 4 divides both. We have 3 options, but we have to see the largest. So largest, you can see it is 4, right? So the HCF of 8 and 12 will be 4. I hope it is clear by the definition of HCF that what is the HCF of two numbers. Now let's see what is the LCM. Least common multiple. Least common multiple. The least common multiple of two natural numbers A and B is the smallest natural number, that is the multiple of both A and B. Now multiple. You know what is multiple? If I say multiples of 2, it means 2, 4, 6, 8 and so on, right? So if I say, let's find out the multiple of LCM. Let's find out the LCM of 2 and 4. Okay, very easy I have taken. Let's see. If I write the multiples of 2, so I have 2, 4, 6, 8 and so on. 4, if I write the multiples of 4, what are the multiples of 4? 4, 8, 12, 16 and so on. So now what is LCM? Least or the smallest natural number, which is a multiple, smallest. If you can see, this is the smallest natural number, which is a multiple. You can see here clearly, it is 4, right? 4 comes in both and it is the smallest. You can see further here, if I go in forward into the table of 2, 2, 4, 6, 8, I am going to get 10 and then 12 also. So 12 is also going to be the common multiple. And then I'm going to get 14 and 16 also. So 16 is also going to be the common multiple. But LCM is the least one, the smallest one. So the answer will be 4. I hope the definition is clear. And further we need to see that the HCF, the highest common factor, it is a factor of the LCM, least common multiple. Okay, so what does this mean? Let's take an example and see. Like here you can see HCF of 2 and 4 is 4. Then what will the LCM? Let's take a LCM. 1, 2. These are the factors. 4 factors. 1, 2, 4. Highest common factor. Highest common factor here is 2. So you can say that HCF of 2 and 4 is 2. So can you see that HCF is a factor of LCM? Yes, because HCF, they are limited. The number HCF of a particular natural number is limited. It is countable. But the LCMs are infinite, right? Sorry, LCMs names. Multiples are infinite, right? The multiples of a number, natural number, are infinite. So here we have, just a minute. It is a very important result that we have, that HCF is a factor of the LCM. And here there is an important relation between the HCF and LCM. Product of two numbers is equal to the product of their HCF and LCM. Okay. So the product of two numbers, if I say here, product of two numbers, if I take the two numbers as 2 and 4, I've got their LCM as 4 and their HCF as 2. So product of two numbers is 2 into 4 is equals to 2 into 4. Can you see it is verified? Yes. I hope it is clear. So this is a very important relation, the relation between HCF and LCM and the numbers. Okay. Let's move forward. Prime factorization. Now, what is prime factorization? We all know. Prime factorization is when we represent the numbers, the composite number in the product of the prime numbers, as a product of a prime numbers. Okay, let's find the HCF and LCM of 12, 48 and 216 using prime factorization. So first let's do the prime factorization of each number. 12, 2, 6, 2, 3, 3, 1. Okay. This is the prime factorization. How do we do? Okay. 2, 4, 2, 12. 2 times 6, 2, 3 and 3 times 1. This is the prime factorization of 48, 216. Let's see. 2 times 108, 2 times 54. Then again 2 times 27. Now this is 3 times. 3 times 9, right? Then this is 3 times 3 and then 3 times 1. I hope it is clear. Now let's write it. Like, how do we write? Okay, 12 can be written as 2 to the power 2 into 3. Yes. How can 48 be written as? 48 is written as 2 to the power 1, 2, 3, 4. 2 to the power 4 into 3. Okay. And how do we write 216? 216. 1, 2, 3. So 2 to the power 3 into 3 to the power 3. Okay, so here the powers of 3 are 1. So in each number, composite number, we have the same two primes. We can see 2 and 3. So first we need to find the HCF, highest common factor. So what do? We take least power of each prime. Okay. And for the LCM, we take the highest power of each prime. Let's see what will come. If I take the HCF first, HCF of 12, 48 and 216. Least power of each prime. So if you take the least power of 2, you can see to the power 2, to the power 4, to the power 3. Least is to the power 2. Okay. And 3 to the power 1 is the least. You can see. So what it will be? 4 times 3, 12. So the HCF of 12, 48 and 216 is 12. And let's see what will be the LCM. LCM of 12, 48 and 216. Highest power of each prime. So we can take to the power 4 into 3 to the power 3. Okay. This is 16 into 27. So this will be the LCM of 12, 48 and 216. Okay. Highest power of 2 and highest power of 3. 16 times 27. Let's calculate. 7 times 6 is 42. 7 times 1 is 7. 8, 9, 10, 11. 2 times 6 is 12. 2, 1, 2, 3. 432. So the LCM is 432. You can see, and you can see 12 is the factor of 432. Is it divisible? Let's see. 12 times 3 is 36. 13 minus 6 is 7. 72. 12, 8 is 72. Yes, see, 12 is a factor of 432. You can see it is divisible. 432 is divisible by 12. So HCF is a factor of the LCM. I hope it is clear. How do we do the prime factorization? Okay. HCF is always a factor of LCM, and factors are limited, but multiples are infinite. Okay. यहाँ पे we calculated HCF of 12, 48 and 216 as 12, and LCM will calculate it as 432. Okay, so this is the answer, and I have told you these both very important points, that HCF is always the factor of the LCM, and the factors of a natural number, they are limited, but the multiples are infinite. Okay, let's go next question. The least number, okay, that is divisible by all the numbers from 1 to 10, both inclusive, is. So now you have to first understand that what you need to calculate in this question, HCF or the LCM. Okay, the least number which is divisible by all the numbers from 1 to 10. So if I will find a number, it should be divisible by 1 to 10, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that number is divisible by every number. So what can we do? We can find a common multiple of all these numbers, and the least common multiple, we need to find the least number. So we will find the least common multiple, which is the LCM, right? I hope it is clear. So we need to find the number which is divisible by all the numbers from 1 to 10, like 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 by each number. Both inclusive means 1 and 10 we need to include. So we need to find what? We need to find a common multiple, right? Common multiple of each of these numbers. And we'll find the least number, so we'll find the least common multiple. I hope this is how you get to know how to solve a question, what is required to calculate in the question. Okay, so now let's find out the least common multiple. If I write 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Let's start. Okay, 2 times 1, 1, 3, 2, 5, 3, 7, 4, 9, and 5. Okay, is there any more 2? Yes, 2. 1, 1, 3, 1, 5, 3, 7, 2, 9, and 5. Okay, any more 2s? Yes. So let's again 2. 1, 1, 3, 1, 5, 3, 7, 1, 9, and 5. Let's go with the 3 now. Okay, 3, 1, 1, 1. Right, 1, then 1, 5, 1, 7, 1, 3, 5. Right, one time more 3. 1, 1, 1, 1, 5, 1, 7, 1, 1, and 5. Then again we are going to have 5 and then 7. I hope it is clear, 5 and 7. So what we are going to get, the LCM of 1 to 10, 1, 2, 3, 2 to the power 3 into 3 to the power 2 into 5 into 7. Okay, so what is this? 8 into 9 into 5 into 7, which is 8 times 9 is 72 into 35. Okay, let's calculate 72 into 35. 5 times 2 is 10, 35, 36. 3 times 2 is 6. 3 times 7 is 21. 6, 6, 12. 3, 1, 4, 1, 5, 2. So we're getting LCM as 2520. And this will be the least common multiple. This will be the number which is divisible by each number from 1 to 10. And this is the least number, right? So our answer is option D, 2520. I hope this question is clear. Very tricky question. You have to understand what you need to calculate. Okay, we'll see many word problems in the future in this lesson, where also you need to observe and analyze that what you actually need to calculate, the highest common factor or the least common multiple. Okay, let's go to the next question. Okay, so this is an assertion reason question which is recently being added to the questions that you will face in the board examinations also, in your pre-boards also. So these questions are a little bit tricky, in which you need to understand the options and how do you go with this question. Let's take a question and see. LCM of two or more numbers is equals to the product of the highest power of each common factor involved in the number. This is our assertion and the reason. Let's first see. Let's first calculate the LCM of 20, 25 and 30. Okay. Prime factorization. We will do prime factorization. 20, 2, 10, 2, 5 and 5, 1. This is the prime factorization. Okay. 25, let's see 25. We all know 25 is 5 square. 5, 5, 1. Okay. 30, let's see 30. 2, 15, 3, 5 and 5, 1. This is the prime factorizations of each of them. So 20 can be written as 2 square into 5 and 25 can be written as 5 square and 30 can be written as 2 into 3 into 5. Okay, where the primes are missing, let's add them with 3 to the power 0 because n to the power 0 is 1, right? 5 square 2 to the power 0 into 3 to the power 0. So we have each of the primes in each of the factorization, prime factorization 2, 5 and 3. So what is LCM? We know. What do we do? LCM will be the product of the highest power of the primes. So 2 we see, if we see 2 to the power 2 is here, 2 to the power 0, 2. So we'll get 2 to the power 2. 5 to the power 1, 5 to the power 2, 5 to the power 1. So we are going to get 5 to the power 2. 3, 0, 0, 1, 3. So it's 4 into 25 into 3. So we know 4 times 25 is 100. 100 times 3 is 300. So we got that LCM is 300. So here we can see the reason given is correct. The LCM is 300. Means it is true, right? But can you see the assertion? The assertion is written the same thing what we did. The LCM of two or more numbers is the product of the highest power of each common factor involved in the number. Each common factor, the prime numbers which are in common factors, they the highest power we have taken, and that's how we have calculated the LCM. This is the right method given. But is this reason satisfying the assertion? Like this is true for the assertion? No. You can see if it had been vice versa, if it had been the opposite, if the assertion was this and the reason was this, then we could have said that yes, both A and R are true and R is the correct explanation. But here R is not the correct explanation for the assertion given to us. Instead, the assertion given is the reason why the LCM is 300. I hope this is clear. You have to observe this. Many students would have done the answer as option A, but that would have been wrong because R is not the correct explanation of the assertion. Okay, so here the answer is option B. Both A and R are true, but R is not the correct explanation of assertion. I hope this is clear. Okay, let's move forward. Okay, so now we are going to do, as I said, now that I told you that we are going to do the questions on HCF and LCM, where we need to be very careful on how we tackle these questions. So some points that we need to remember while tackling the word problems on HCF and LCM is, read the question carefully. Yes, you need to read the question very, very carefully, analyze what you have to do in the question, what is given in the question. Okay, then we have to observe and guess if the answer will be greater than or lower than the given data in the question. You need to observe and you need to analyze that what will be the answer. Will the answer be less than the data given in the question or more than? And HCF of students is students. This means that whatever the thing we are calculating, if we are calculating the HCF of 2 pen, 5 pens and 6 pens, then the HCF will also be pens, right? Whatever HCF is, right? So if I say 2, 5 and 6, what will the HCF? You can say the HCF will be 2, 5 and 6. The HCF is 1. I hope this is clear. Means the whatever will be the HCF will be also the pens. Okay, now let's see the questions. 3 alarm clock ring their alarms at regular intervals of 10 minute, 15 minute and 20 minute respectively. So there are 3 alarm clocks and they are ringing alarms at the regular intervals of 10 minutes, 15 minutes and 20 minutes respectively. If they first beep at 12 noon, so they first beep at 12 noon, all the 3. At what time will they beep again? So we need to calculate at what time will they beep again. Okay, so first we have read the question carefully. Now we need to observe. If I think that if the alarms have beeped on 12 noon, okay, so can it beep again together at 5 minutes? No. Why? Because 5 minutes this alarm will not beep, neither this will beep, nor this will beep. Okay. Can it beep at 12 minutes? This will beep, but this will not beep, neither this will beep. So we can see that clearly the answer will be greater than the three numbers given to us, right? The answer will be greater than the three numbers which is given to us. So the three numbers which is given to us, the answer will be greater. So we can see that if the answer is greater, so of course we need to find a multiple, right? We need to find a multiple, because the factors are always less than the given numbers, right? The factors are always less than, or they can be equal to, but they will never be greater than the given number, right? So we want the answer to be greater than the three of them, because they have to be. If it is less than any one, then either one of the alarm will not beep, right? So they have to be greater than all the three numbers. So we need to find the multiple. We got the answer here. That's why we need to think that the given answer, the answer that we will get, will it be greater than the given data or less than the given data? Okay. And why do we need to find the least? So here we get to know that we need to find the LCM. But why least? Because there are many instances where they will beep again. But we just want that after 12 noon when they will beep. Okay. For the first time. So now let's clearly find the LCM of 10, 15 and 20 minutes. And the answer, if we are going to find the LCM of 10, 15 and 20, the LCM will give us minutes. Okay, so in the question it is asked time. So we need to calculate the time. Okay, so let's find the LCM. 10, 15 and 20. 2, 5, 5, 1. 3, 5, 5, 1. 2, 10, 2, 5 and 5, 1. Okay, so 10 is 2 into 5. 15 is 3 into 5 into 2 to the power 0 you can write. And 20 is 2 times 2, 2 square into 5 into 3 to the power 0. What is here missing? 3 to the power 0. So LCM, we know highest, right? Highest power of each prime, or you can say each factor. So LCM will here will be 2 to the power 2 into 5, we can see 5 into 3. Okay, so 4 into 5 into 3, 20 times 3 is 60 minutes. So we have got 60 minutes as our LCM. So they will again beep after 60 minutes. So if it's 12 noon, after 60 minutes, that is 1 hour. After 1 hour, it will be 1 p.m. So the three alarms will beep again at 1 p.m. I hope this is clear, right? Because we got 60 minutes as the LCM, it means that after 60 minutes, they will beep again. And they first beep at 12 noon. So 60 minutes is 1 hour, right? So we do 12 plus 1, which is 1 p.m. They will beep again. I hope this is clear. Okay, next question, let's see. A fruit basket, okay, a fruit basket has 850 apples, 925 oranges. He packs them into baskets. Each basket contains only one of the two fruits, but in equal number. Okay, so each basket is now containing only one of the two fruits, like only one variety. If one basket has apples, then it has apples only. If one basket has orange, then it has oranges only. But each basket has equal number of fruits. Okay, find the number of fruits to be put in each basket to have minimum number of such baskets. So we need to put the maximum numbers which we can put equally in each basket, so that we use minimum number of baskets. So here first of all we need to understand the answer that we will get. Will it be less than the given data or greater than the given data? Okay, so if you're thinking, let's see, 850 and 925. We have 925 oranges and 850 apples. So of course we need to find the minimum number. So we will divide something. Like if I do 850, if I divide 850, it's divisible by 2 also, right? It's divisible by 4 also. So if I write in different ways, taking the factors or which it has, there will be some which will be left, right? So I need to find the highest common factor. I need to find the common factor of both the numbers. Okay, and then I also need to find the highest common factor. Because if I find the highest common factor, then only minimum number of baskets will be used, right? So now let's first find the highest common factor. HCF of 850 and 925. Let's see. 850. 2 times, if I do 2, 4, 2 2s are 2 2s are 4, 10, 425. Okay. Is it going by 3? 4 to 7, 7, 5, 12. Yes. 3, 12, 4. Is it? 4 to 7, 7, 5, 12. It is. 3 times 1 is 4. 3 times 1 is 3. 1. 14 3s are, yes, it is. 4, 5, 6. Oh no, it is not going by 3. Okay, I'm sorry. It is not going by 3. We need to do it by 5 only. 5 times. Okay. 4 times, yeah. So 5 times 8 is 40 and 5. Then again 5, you can see. Okay, if I see 5, then it is 17. 17, yes. And 17, 1. Because 17 doesn't come in any other table, it is a prime number. Okay. If I do of 925. 925, 9, 10, 11. 11 plus 5 is 16. It's not going by 3. So it will go directly by 5 only. Let's see. 5 times 1 is 5. 42, 8 and 5. Then again 5. 18. 3 times 15, 37. And we have 37, 1. Because 37 is again a prime number. Will not go by any other number. Okay. So we can write 850 as 2 into 5 square into 17. And we can write 925 as 5 square into 37. Okay, so what are missing? Let's write the missing primes first. Here it is, the missing number is, I think, 37 to the power 0. And here we have missing as 2 to the power 0 into 17 to the power 0. Now, we know that HCF is the least power of the common primes, right? Least power, let's see. If I take 2, the least power is to the power 0, that is 1, right? Yeah. And if I take 5, 5 is 5 square. Okay. So 5 square. So I think it's 25. Yeah. So 25 is the HCF. But the 25 is number of oranges or apples. Okay. Number of oranges or apples. So it means that you can divide 850 apples into 25 apples, right? 25 apples. So how many baskets do we need? So if I divide 850 by 25, how much I am getting? 25, 3 is a 75 and 4 times 100. So we are getting 34 baskets will be needed for apple, and for 925 oranges. So how many baskets will we need? 25. Again, 3 is a 75. 75, 85. 85 plus 10 plus 17. 175. Right? 175. It's 4 times 100. 6 times 150. Right? And 7 times. I think it's 7 times 175. 25 times 7. 7. Yes. It is 175. Okay, 37 baskets are required for oranges. So how many total baskets are required? Total baskets will be 34 plus 75, which is 7, 9 and 7, 3, 10. So minimum we need 109 baskets. Oh, I'm sorry, this is 35. Let me do it again. 34 plus 37. So 7 plus 4 is 11. 3 plus 3 is 6, 1, 7. 71 baskets. 71 baskets we are going to require for putting the fruits in the baskets, such that each basket contains only one of the two fruits but in equal number, and we use minimum number of baskets. I hope this is clear how we have done this. We have approached this question. So we need to find the common factor. Okay, we needed to find the common factor because we needed to know what is the number which divides both the numbers 850 and 925. Okay, that's the way we can keep the same fruit in the baskets. Okay, so I hope this is clear why we did that. Okay, now let's revise what is real number. Okay, real number, you all know. We know rational numbers and we know irrational numbers. So they both together comprise of the real number, right? So we can say that real number is actually rational number plus irrational number, right? It is whole. Now let's see further. We already know this. I'm just giving you a review of it. Okay, so rational numbers, we know rational numbers. Rational numbers, what are rational numbers? P by Q form, where P comma Q belongs to integers and Q is not equal to 0, right? Rational numbers, right? And they contain integers. Integers are contained in rational numbers. And then we know that whole number is contained in integers and natural number is contained in whole number. We all know this, right? So the rational numbers, if I write, so integers, what are integers? We know the negative natural numbers, -1, 0, 1, 2, and this entire is integers, right? What are the whole numbers? Whole numbers we know from 0, 1, 2, 3, and so on. And natural numbers are 1, 2, 3, and so on. So you can see that the natural numbers are contained in the whole numbers. Whole numbers are contained in the integer, and the integer is finally contained in the rational number. I hope this is clear, right? Yes, we can see it clearly. The natural numbers are contained in the whole numbers are contained in the integers, and integers are contained in the rational numbers. And these whole comprise of the rational number. So is every rational number an integer? No. Is every rational number a whole number? No. But we can say that every whole number is a rational number. Every integer is a rational number. Every natural number is a rational number. Okay? Not vice versa. I hope this is clear, and we have already learned this. So now we are going to go with the irrational numbers. Like here I told you what is irrational number. Irrational numbers, we usually depict them as the square which is not a perfect square. The square roots which are not the perfect square, or the cube roots which are not the perfect cube, right? You can say cube to the power 7, or you can write cube 7 or root of 7.9, right? Anything which is not a perfect cube, or in sense which is not a rational number. A number which is not a rational number is a irrational number. A real number which is not a rational number is an irrational number. And we also learned the decimal expansion. For the rational number, we know the decimal expansions must be either terminating or non-terminating and recurring. Recurring, recurring, it means repeating, right? Example, if I take 1.3 bar, or which is equals to 1.333 and so on. So this is a recurring number, repeating decimal. Okay, recurring decimal. And what are irrational numbers? Irrational numbers, they are depicted as non-terminating and non-recurring. We have an example of it, pi, right? Pi is a transcendental, right, which has a value of 3.14 ... in which all the digits are not repeating. None of the digit is repeating. They all are separate and they don't form a pattern, right? So that is non-recurring. So irrational numbers, their decimal expansion is non-terminating and non-recurring. I hope it's clear. Let's move forward now. Yes, so we have came to the last topic and the most important topic of this lesson, which is the proof of irrationality. Before we start with this, I will introduce you to important terminologies and to important concepts that we are going to use in the proof, that how do we prove the number is irrational. Okay, so first we have co-prime. So two natural numbers are co-prime numbers if they have no common factors except one. Okay, so we need to keep in mind. Now you will say, ma'am, 2 and 3, they both are co-prime. How do we come to know? 2 has two factors, we know 1 and 2, right? 3 has two factors, 1 and 3. The common factor is 1. So yes, 2 and 3 are co-prime. Okay, in the similar way, you can say that is 4 and 9 co-prime? If I see, 4 has how many factors? Let's write 1, 2 and 4. 9 has how many factors? 1, 3 and 9. The common factor is 1. The common factor is 1, right? They co-prime, we have prime in this word, but it doesn't mean necessarily means that two natural numbers that we are taking must be prime. Like here you can see 4 and 9 are not prime numbers. You can see it clearly because they have more than two factors. They're composite numbers, right? But they are co-prime numbers. 4 and 9 are co-prime. So prime is not related to co-prime. Okay, so two prime numbers can be co-prime, but every time if two numbers are co-prime, they must necessarily not be prime numbers. You can see that. This is an example of it. Okay, I hope this is clear. We have to keep this in mind. And the second important, very important result is that if P is a prime number and P divides A square, then P divides A, where A is a positive integer. So we need to keep this very, very much in our mind that if we have a prime number, like if I see that if I take 4, 4 is A square, right? It is 4. If 2 divides 4, yes. And what is A here? If you have taken A square as 4, then A we know is 2. So 2 divides 2 also, it is 2, right? So you can see why, because 2 is the it comes in the prime factorization of A square also and A also. That's why. Okay, the prime we are taking, it will come in the prime factorization of A square also and A also, and therefore it will divide both A square and A. These two are the many very important points that we need to take in mind while we are doing the proof of irrationality. Let's see now how do we proceed. Now here is a question in which we need to do what we need to do. We need to prove that root 2 is irrational. We know this, right? We know that root 2 is irrational. Here it is asking us to prove it. So how do we approach this question? We'll do it with the help of the contradiction method. Contradiction method. We will assume otherwise. We will say that let us suppose that it is not an irrational number. Let root 2 be a rational number. Okay, let 2 be a rational number. So how can we write root 2? We know every rational number definition is P by Q, where P by Q belongs to integers, Q not equal to 0. And here we take one thing more, that P and Q are co-prime. So it means we are taking the rational number in the simplest form. It means P and Q has no other common factor except 1. We need to keep this in mind. Okay. Okay, now we have this. So let's proceed further, do some mathematics. Okay, if I say, then we can write P is equals to root 2Q. If I square both sides, squaring both sides, what will I get? P square is equals to 2Q square. Okay, so you can see P square is equals to 2Q square. P can be written as some multiple of 2. This means that 2 divides P square, right? 2 divides P square. And this implies 2 divides P. Here we did a result that if a prime divides A square, implies that the prime divides A, right? So we can say that if 2 is dividing P square, because P square is written as some multiple of 2. So of course 2 divides P square, and we can write 2 divides P. So now again, if 2 divides P, then P can be written as some 2C, okay, where C is also a integer, right? So p can be written as 2c, because if it divides p, of course p is a multiple of 2. Now we will put this, let's mark it as second and let's mark it as first. Putting second in first. What will we get? We will get 2c square is equals to 2q square. This implies 4c square is equals to 2q square. Okay, so what we are getting? We are getting that q square is equals to 2c square. Oh, so now here we can write that actually 2 divides q square also. This implies that 2 divides q. So now you need to give attention to the fact that 2 divides p and 2 divides q. This means that p and q have 2 as their common factor. Right? They are having 2 as a common factor, which is a contradiction, because we assume that they are co-prime. It is a contradiction, right? We have assumed here that p and q are co-prime. It means that they have no other factor except 1. But here we have taken out that 2 is their common factor. So of course we have done something wrong. What is wrong? Our assumption. Our assumption is wrong. So we will say that our assumption is this means that root 2 is not a rational number. And what does it mean? If it is not a rational number, then it is a irrational number. Irrational number. You see how cleverly we have used the two important results or the concepts that I told you prior to this. Here we have used that they both are co-prime, and we have made a contradiction on the fact also that they are co-prime. It means that they will not have any other common factor except 1. But while solving, we got to know that they are having 2 as their common factor, which is not possible because we have assumed that. So we have assumed wrong. And what did we assume? That is a rational number. So it means this is a contradiction. I hope this is clear. Let's do one more question. Prove 7 minus root 5 is irrational if root 5 is irrational. Okay, so here actually the question has been made easy for us because it is already given in the question that we have to assume, we know that root 5 is irrational. Okay, so if root 5 is irrational, let's proceed normally. Let 7 minus root 5 be a rational number. Okay. If I take it as a rational number, then 7 minus root 5 is equals to some p by q again, where p and q are co-prime and p comma q belongs to integer and q is not equal to 0. This we need to keep in mind. Very important assumptions are these. Okay. Okay. So what can we see? Let's take p by q here and root 5 here, because we know that root 5 is given to us irrational. So what we will get here, 7q minus p upon q is equals to root 5. Can you see some contradiction here? Can you? Yes, because you can clearly see that this whole thing, because since p and q are integers, so of course anything we do will get an integer because integers are closed. They follow the closure property, right? So we can see this is also an integer and this is also an integer. Integer by integer, this is a rational number. This is a rational number, right? While we are given in the question that root 5 is irrational. So this is wrong. So we can say that this contradicts, okay, our assumption. So this implies 7 minus root 5 is also a irrational number. I hope this is clear to you. How do we proceed? And if it would have not been given to us that root 5 is irrational, we first have to prove that root 5 is irrational. Okay, and then we can proceed further with this question. And how will we prove that root 5 is irrational? In the similar manner as we did for root 2. Okay, you will get a number of, I think you will get 5 only, which will be a common factor of P and Q, which will contradict the fact that P and Q are co-primes, or you can contradict, and which in turn will contradict the fact that root 5 is a rational number. Okay, I hope this is clear. How do we approach such questions and how do we do such questions? Okay, let's summarize the lecture today, the sessions we did. So we first learned the fundamental theorem of arithmetic, which said that a composite number, it can be expressed or factorized as the product of prime factors, prime numbers, and the factorization which we get is unique apart from the order in which the prime factors are taken, right? Which is very important. We learned about various different kinds of numbers. What were the numbers that we learned about? Composite numbers, prime numbers, co-prime numbers. We also learned the relation between HCF and LCM, which was that product of two numbers is equals to product of their HCF and product of their HCF and LCM. Right? Very important. What is HCF and what is LCM? We also revised prime factorization. We also revisited the real numbers. Right? We revisited that real numbers and irrational and rational. How do we know that if a given real number is rational or an irrational number? And then the most important topic that we did was proof of irrationality. We also did some good questions, word problems on HCF and LCM, in which we remembered that we need to first observe the problem very carefully. Then we need to observe that and guess if the answer that we're going to get should be less than or greater than the given data in the question. And we also know that whatever we are calculating, it will have the same unit as the data given in the question, as the data for which we are calculating that particular HCF or LCM. Okay, I hope this is clear. I hope this lecture will help you to gather some more information for real numbers and revise your real number chapter very thoroughly. Thank you so much. If you like my lecture, please like and subscribe. Thank you.